Hello everyone, welcome back to our NLP series. Today we are diving into the captivating world of sequence to sequence models. Have you ever wondered how machines can understand languages and even translate them? Sequence to sequence model holds the key to this magic. They are the superheroes of sequence prediction task from language modeling to translation. In this session, we will uncover the secrets of sequence to sequence models, how they work, their network architecture, real world applications, and most importantly, how to build them using Keras. So, buckle up as we embark on this exciting journey into the realm of sequence to sequence modeling. Moving on, sequence to sequence model consisting of two parts, encoder and decoder, which can be either RNNs, CNNs, or transformer networks, whatever it may be. In this architecture, here the encoder processes the source data sequence of items one at a time and generate the final hidden state information as a context vector, which will then be the input to the decoder. Then the decoder starts generating the target sequence tokens one at a time as an output. This is the overall idea of sequence to sequence model. Thus, sequence to sequence models used to map the sequences of input to the sequence of output, where encoder takes the sequence of items and a decoder outputs another sequence of items. Thus, we can say these are the special class of recurrent neural network architectures which are typically used to solve more complex language problems such as language translation, nothing but the translating from one language to another language, question answering, chatbot conversations, text summarization, etc. etc. Let's see the language translation problem, which is called as the neural machine translation task of sequence to sequence model. This is the neural machine translation task of English to Telugu language translation. So, looking at this, at time step 1, the encoder takes the first token of the input sequence and generates the hidden state 1. Along with the hidden state information, hidden state 1, it will take the next token of the input sequence at a time step 2 and generates the hidden state information 2. This hidden state information along with the third input token of the will be processed at the third time step, which will generate the third hidden state information, which is the encoder, which is the output from the encoder part, or the final hidden state information from the encoder after processing all the three tokens in the input sequence of text. And this hidden state information will be the final outcome of encoder, which will be fed as an input to the decoder part at the next time step 4, which is nothing but the context vector fed to the decoder part. Now, from this decoder, at the next time step, it will start generating the tokens one at a time for the output or a target language sequence tokens will get generated one at a time. Thus, the decoder generates the first target language Telugu token memo at the 5th time step, and in the next time step, it will generate another next token in the sequence. This process will continue until the last token, that is the end of the token of the target language, is generated. This is how the NMT will works to translate from one language to another language. So from the English language, from the sequence of tokens, who are we? The encoder decoder part generated the target language tokens, that is the Telugu tokens, 2 tokens, memu evaramu. Let's see an example. Imagine that you already trained an NMT system, and this is how it would behave in the test time. At different time steps, you feed the tokens, and this is from the feed the tokens from source language sentence, and the last hidden state will have the encoded version of the entire sentence. This context vector is the initial hidden state information to the decoder, and this will produces the first output miru, and that will be directly fed as a input to the next hidden state, and which will produces the output ella, the next token ella, and this will be fed as an input to the next hidden state, and it produces the next token, and this process continue until it will generate the end of the token in the target language. Thus you can say that the encoder produces the encoding part of the source sentences which is available at the hidden state, and the decoder RNN is a language model which generates the target sentences conditioned on encoding. Thus this is called the conditional language model, because the decoder is predicting the next word of the target sentence y, and its predictions are conditions on the source sentence x. Thus this NMT directly calculates the probability of y given x, which is the probability of y1 given x times of probability of y1 given x times of the probability of y2 given y1 and x, which is it times of the probability of y3 given y1, y2 and x. Here this y1 is the first predicted word given the input context vector, and this is y2 is the next word to be predicted given the previous predicted word from the target sentence y1 along with this context vector of the input times of the probability of the next word to be predicted given these two previous two words predicted y1 and y2 along with the context vector, and so on. So that basically this is the probability of next target word given the target words predicted so far and the context word vector of the input sequence. Now let's talk how to train an NMT system. In order to train the NMT system, we need to have a big parallel corpus. Here parallel corpus means which is a collection of parallel sentences from both the sources and the target languages, source and target languages. Now what we need for training the sequence to sequence model is, here are the 3 points you need to remember. For the decoder, during the training, provide the input from the corpus no matter what the decoder produces, and the output of the decoder is only used for calculating loss. Here we are not going to feed back into the hidden states, next hidden states. And during the testing, the output of the decoder is given as an input to the next time step. Let's deep into the training process of this NMT system. We feed source sentences tokens at different time steps that is encoded at the last hidden state, and this is the input for the decoder which produces the first output y1, and we calculate the error j1 here. It is the negative probability. This error is the difference. This error J1 is the difference between the actual word in the sequence miru and the produced words y1 by this layer. The difference between this y1 and the actual word v2 is the error J1. We use this difference to update the weights of all these hidden states. So this is nothing but the back propagation. So after producing the first word y1 and calculating the error z1, then we feed back the actual word miru to the next hidden state, and we don't feed the same output y1 to the next hidden state. Please remember this point. We continue this process and we calculate the next prediction y2, and the error j2 was calculated for the second word, and we back propagate till the beginning. This is how the training of NMT system will work. Let's move on to the demo part. So coming to the demo part of English to Telugu machine translation task. In the first step, we imported all the required libraries from the TensorFlow Keras. We imported the model and the layers which are required, input LSTM and the dense layers. Once this is done, and the next step is we need to create the English to Telugu dataset, which is the sample dataset, what we said, the parallel data corpus is required. As our task is translation from English to Telugu, so we took the set of English sentences and the set of Telugu sentences as well. Here are the three sentences I took for as a sample data set. Okay, once the data set is created, the next step is we need to create the dictionary to map these words to the indices of both the languages English and Telugu. So for each word in the English sentences which is splitted on the space, we are creating a dictionary with the word and the corresponding index. Done with this part. I'm running the code cells simultaneously. So once this is done for the English, similarly we supposed to do it even for Telugu as well. But for here is an additional point is required while creating the dictionary for word to index for the target language, whether it is the English or French or whatever it may be, Telugu or whatever it may be. For the target language sequences, an additional step is required while creating the dictionary which maps the words to the indices. What is that? Is in the target language, this decode is going to start generating the target languages. It doesn't know where to start and where to end, where to stop the generation. So for this, a special tokens, both the start and end tokens, to be assigned to the whatever the target language that we are using in the NMT concept. So for the first for generating Telugu word to index dictionary, we took two special tokens. That is, one is the start and second is the end token, which is added at the beginning itself. And then similarly, whatever is done for the English word to index, the same is repeated even for the Telugu language. So once this is done, just have a look on how these dictionaries are looking like that. Look at that source sentence is having all the words and starting with the index 0 to 10. All the words in the source English language are indexed from 0 to 9, so that there are 10 unique words are there in the English language, English sentences that we have taken as the sample data set. Similarly in Telugu, there are, so you can observe here, this is the start token is indexed 0, end token is indexed 1. Along with that, the rest of all the unique words in the Telugu have been assigned the indexings. So that finally totally we have 0 to 14, means 15 unique tokens are there in our Telugu vocabulary. Once this is done, the next step is we need to set the parameters. In order to set the parameter, what are the parameters we set it here are the number of encoder tokens, number of decoder tokens, and the maximum sequence length. Encoder tokens means the input for the encoder is English, so total unique words in the English sentence, total unique words in the Telugu sentence was calculated, and these are the number of encoder tokens, number of decoder tokens, and the maximum input sequence length, English sequence length is calculated, and the maximum decoder, nothing but the Telugu sequence length have been calculated. And finally, the latent dimension is we are going to use the RNN, that is the LSTM layer, with the number of hidden states, 256 nodes in the LSTM layers. So the latent dimension defined for the LSTM is 256. We already saw that there are a total of 10 English words and 15 Telugu words, unique words. This is what 10 and 15. And the maximum English sequence length is 4 words, and the maximum Telugu sequence length is 5. You can see here, machine learning సరదాగా ఉంటుంది, నాకు కోడింగ్ అంటే చాలా ఇష్టం. This is the maximum sequence length in Telugu with 5 words. This is what it is given. Fine. And then the next step is we need to initialize the MTRs for the encoder and decoder input data. The size of these encoder input data, decoder input data, and decoder target data, all these three input arrays to be initialized with the np.zeros. So what are the shapes? These are the 3-dimensional matrices. What are the shapes that we are taking is the total number of input sequences, English sentences, and the maximum sequence length, that is what 4 we got it here, and with the total number of encoder tokens, that is what 10 in the English. The same is to be done for the decoder input data. For the decoder, we are passing Telugu languages. So total number of Telugu sentences and the maximum decode Telugu sentence length and the maximum tokens into Telugu. The same is the output for the decoder target data. Similar is the decoder target data. Right. We can say that. So encoder will be given English sentences and decoder part will be given Telugu sentences. This is what we did it here. Let it run. Now coming to this part. And the next step is we need to populate the encoder and the decoder input data. Let's break down this code. We are iterating through the pair of English and Telugu sentences. For each of the English sentence, which is splitted in terms of words into words, for each of these word, we are finding its index position and setting the corresponding position in the encoder input data matrix to 1. This is nothing but one hard encode representation where each word is represented by a vector of zeros except for the position corresponding bits to the index which is set to 1. Okay, so this result is a matrix. You can see the 3 dimension. This result is a matrix where each row represents the English sentence and each column represents a word in the vocabulary. The same is done even for the Telugu as well, that is the decoder input data. But in addition to this decoder input data, we have to set the decoder target data is also similar to like this, except an additional part. Additionally for this, what we did is for the target data, we are shifting this target sequence by one position to the right, excluding the targeted token. So this is because the decoder is trained to predict the next word in the sequence. So we provide it with the correct previous word as an input during the training. Therefore, we set the target data at position t minus 1 to 1 for each word in the Telugu sentence, excluding the first word corresponding to the starter token. That is the difference. This is how we populate the encoder and decoder input data for both encoder, decoder and decoder target data. Once this part is done, then we need to look into the defining the input and the sequences for the processing it. This is the code which is setting up the encoder part of the sequence to sequence model for English to Telugu translation using LSTM. In both encoder and decoder parts, we are using the recurrent neural network LSTM. Fine. So let us look into this encoder part. Here this is the input layer where the encoder part with the shape and the number of encoder tokens. Total number of tokens in the English sentence is 10. So thus the input layer is defined. Now this LSTM layer is defined with the latent number of dimensions 256, which we have taken in the very beginning of the steps, and setting the return state equal to true. For the encoded part, we don't want the LSTM layer to return the hidden state at each time step. We want the LSTM to return the hidden state information at the last time step only. So we set the return state only to true. So which will return the final hidden state information only by the LSTM layer. This is how this encoder inputs and LSTM layer has been defined and stored into the variable encoder inputs and encoder. Now this encoder inputs is assigned to the encoder layer, which will generates the encoder outputs along with the hidden and cell state information by the LSTM layer. We are storing this hidden and cell state information only because into the variable encoder state, because we don't want the outputs from the encoder part. Only state information we need, so that's what we stored into the variable encoder states. This will be used for the decoder part. Okay, now let's moving on to this decoder part of the sequence to sequence model. So while breaking down this code into the part by part, this defines the input layer for the decoder, which specifies the shape of the input data that the decoder will receive, and this none represents the variable length of the input sequence, and the number decoder tokens is the nothing but the total number of tokens in the target, nothing but the Telugu vocabulary. And the next is, this is the LSTM layer, which defines LSTM layer for the decoder part with the latent number of dimensions, nothing but the output dimension of the LSTM layer, number of units 256 that we have defined. And we set the return sequence is true. In the decoder part, we need all the outputs from, we need the output from each of the time steps. So we set the return sequence parameter equal to true, which is nothing but which is false in the encoder part. That is the difference. And along with this return sequences, we want the final output as well, final hidden state information as well. So we set the return state parameter is also to true. Once this is done, then we applied this decoder LSTM layer with the decoder inputs and the initial states, which is taken from the encoder part. That is, encoder state information is the initial hidden state information to the decoder along with the decoder input information. Then this decoder information is nothing but the total number of tokens in the target language, nothing but the Telugu. Thus the decoder LSTM layer has been implemented and the results were recorded here. Next, this is the dense layer with the softmax activation is defined. A dense layer with the softmax activation is defined with the decoder number of tokens. And so this dense layer has been applied to the to get the final output to the decoder outputs, which will give the final outputs. Nothing but it will generate the final output of the decoder by applying the dense layer to the output of the LSTM layer. Once this is done, then now we have defined both the encoder part and decoder parts. Now let's moving on to the defining the model which will run both the encoder input, decoder input, and along with the output is decoder target data. So the model is defined with the input features is a list of encoder inputs and decoder inputs, and the output is labels or the output is nothing but the decoder outputs. Once the model is defined, we compile the model by specifying this optimizer, RMS prop, and categorical cross entropy as the last function, and the measuring the accuracy. Once the model is compiled, we train the model with the encoder input data, decoder input data as a list which is the input to this part, and the decoder target data is the output. Whatever the model is defined is the same way the data model was trained. With the batch information of 64 for 100 epochs we are running, and with the validation splitting is 20%. And we saved this model, whatever is the trained, for further use for inferencing without retraining the model again and again. Let's coming to the part. Yes, we ran the model, and already I just before starting this session I ran this model with the 70% of accuracy we got it. Let's leave on to this. Now let us move on to the inferencing this model. So let me give a brief of what is that inferencing. While inferencing the models like NMTs, there are sequence of steps to be processed. So those are, first is the loading the trained model, fine. Then defining the inference models. What is the need of, you might have a question of what is the meaning of defining. Again, we have to define this encoder and decoder models for inferencing. You might have a question of, already we defined encoder and decoder parts of the model in the previous step. We compiled and trained here itself, right? Yes, here itself. Already we defined, we compiled and trained the model itself. But still again for inferencing, why are you defining this inference models again, encoder and decoder modes? The answer for this question is, during the task like machine translations, in training the encoder and decoder are trained together, with the encoder receiving the input sequences and the decoder receiving the target sequences. However, during inference we need to use the encoder to encode the input sequence and then use the decoder to generate the output sequences. So obviously here is the requirement is we need to define the separate encoder decoder inference models. That is the mandatory steps. Fine. Okay, this is the second step, and then we need of this dictionaries which maps the indices back to the readable characters for both the source, nothing but English and Telugu languages. Once these reverse lookups have been created, decoder sequence function is to be defined, which will decode, which will perform actual decoding. Then finally decoding the sentences whatever you want to do. Let's do the translation. These are the 5 steps in inferencing an NMT model. Okay, let me back to this inference model, defining the inference models part. So in the inference model parts, first is this model takes the encoder inputs and returns the encoder states. Here the encoder inputs is nothing but the English words, and hidden these outputs, encoder states, are the hidden and cell states of the encoder LSTM, representing the encoded context of the input sequence. Once this is done, then coming to this part of the decoder, decoder model for inference. Now these two are the placeholders, input placeholders for the decoder LSTM states, hidden state and cell state. Once these two are defined, then the next step is decoder inputs, decoder state inputs to be calculated, and the list of these two encoder states and list of these two are the decoder states which are initialized with these two. The meaning that hidden and cell state information placeholders have been created, and we are defining that as the decoder states inputs initialization. Now these decoder states to be calculated after applying LSTM layer, decoder LSTM. That's what we did in the next line of the code, decoder LSTM. Yes, decoder LSTM. This runs the decoder LSTM using the decoder inputs, initial states. What is this decoder inputs? Is the input sequence of the Telugu words, and these initial states, which are the decoder states, are the initial states of the decoder LSTM. This initial states of the decoder LSTM. And now this list is the decoder LSTM output states, hidden and cell states. These are the list of decoder LSTM output states. Now this decoder dense layer, this passes the decoder LSTM outputs through the dense layer to obtain the final decoder outputs. Okay, right. Next, this line of code defines the model, nothing but the decoder model, which takes the decoder inputs and the initial states and returns the decoder outputs and the states. This is how we have to define the inference model for both the encoder and decoder parts. So here the inputs is the decoder inputs and initial states, and output is the decoder output and final states. Now this is the code which will create the dictionaries, which allows the reverse lookup for token indices to decode the sequences back to something readable format for both the sentences, both the languages, English and Telugu, source and destination languages. Now this code defines the decode sequence, which is responsible for generating Telugu sentences from the given English input sequence using the trained encoder decoder model. Let's look into the lines of code in this one. The first is this line of code. This encodes the input sequence, nothing but the English sentence, into initial states using the encoder model. So that's why you call the encoder model dot predict on the input sequence, that is the English sentences. Thus the input will be encoded into the state vectors. Now, and the next step is, the first we initialize the empty target sequences np.zeros. Then this sets the first character of the target sequence to the start token, and this is a sampling loop. This loop generates the Telugu sentence token by token until it reaches the end of the token or the maximum length. So if you go inside this loop, let us see this. This predicts the next token in the sequence using the decoder model and the previously generated token and states. I'll repeat again. This line of the code helps to predict the next token in the sequence, output tokens, using the decoder model. So decoder model dot predict is being used, and the previously generated token and states. Previously generated target token and state value based on this decoder model predict the next token in the sequence. This is the main logic of the code that we discussed on the slides. Okay, then coming to the next, this line of the code will select the token with the highest probability from the output distribution, and this maps the token index back to the Telugu word using the reverse dictionary, and this line of code appends the decoded word to the decoded sentence. Right, then this is the last part of the code in the loop, which helps to check the stopping condition which occurs when either the end of the token is arrived or the sentence reaches to the maximum length. That's it. Okay, once this is done, then this target sequence and states will be updated by these two lines of the code. This will update the target sequence with the predicted token for the next iteration, and this updates the states for the next iteration, and then finally it returns the decoded sentence. So this is the step of decoding the sentence function, decode sequence for the given input sequence. And okay, we reached to the last step of inferencing an NMT model, that says finally doing the translations. Coming to this part, loop through the each English sentences. Here I have taken the entire, I took only the sample database with the 3 English and 3 Telugu sentences. The same is used for translation, for testing the trained model. So already we loaded the trained model. This loaded trained model is being used for testing this. This is what I am showing here. Okay, from the English sentences, for the sequence index in the range of, for each of the sentence in the English sentences, we are doing this part of the course. So this loops iterates through the over each English sentence in the data set. So this part, this selects the input sequence English sentence from the preprocessed encoder input data. Preprocessed encoded input data. It selects one sequence at a time using this slicing. Okay, right. Now this will be decoded. This line of the code calls the decoded function to generate the Telugu translation for current English sentence. Decode sequence is a function that we had defined just prior. So for this input sequence which has been generated, this will be passed to the decode sequence function, which will generate the decoded sentence, which is nothing but Telugu translated sentence. Those two things we are displaying here. So once I ran this code cell with a sample of data for the input given, for the sample of data of 3 sentences that I have taken, I love coding, machine learning is fun, AI is the future. We got the translated, I love coding, the decoded sentence is coding only, it has generated only one word in the target sequence, Telugu, and machine learning generated, AI is the future, Medha. So Telugu translated Krutrima Medha, future, Bhavishyattu, Medha anedi, it generated 2 tokens in the Telugu. And again I ran this code cell with added two more sentences like Python is versatile and data science is the demand. So just have a look on how these two were translated. Python is versatile. It returned the decoded center Bahuvida. The versatile is the Bahuvida. It's correct one word it had written, but for this it is the wrong predictions it made. The data science is in demand, but it written Bahuvida only. And learning new skills is rewarding. For this is also wrong predictions. Anyhow, it is generating the uh, Telugu language sentences from the English language input language. So you can train. So here I used the same trained model for another new data set as well, so that I got these outputs. So this is all about neural machine translation from English to Telugu. Hope you understood what is the strategy of translating one language to another language using the NMT using recurrent neural networks.